Good morning, everybody. Please take a seat. Welcome to the KIOS Distinguished Lecture in memory of Professor Elias Kyriakides, which this year is going to be given by Professor Nikos Hatziargyriou. Before I introduce our distinguished lecturer, I would like to say a few words about our dear colleague Elias Kyriakides, who passed away 4 years ago in October of 2019. Professor Elias Kyriakides was a leading expert and a rising star in the areas of electric power systems and critical infrastructure systems, with an emphasis on wide area monitoring and control, power systems operations, and the integration of renewable energy sources. He received his PhD degree in electrical engineering from Arizona State University in the US in 2003. And he worked there as a faculty research associate until 2004. In 2004, he became a member of the faculty of the electrical and computer engineering department at the University of Cyprus. He was actually one of the first faculty in the department. The department was initiated in 2001 and admitted the first students in 2003. So Elias was one of the first students, one of the first faculty to join the department. Elias was also a co-founder of the KIOS Research and Innovation Center of Excellence, and one of the reasons for the many successes of the center. Elias published more than 200 papers in high-caliber refereed journals and international conferences, and served as a coordinator for several national and international projects, European projects, and as a partner in others. He was the coordinator of the cost action, intelligent monitoring, security, and control of critical infrastructure systems, IntelliSys, which was the first cost action to be coordinated by somebody in Cyprus. He served as an associate editor for the IEEE Systems Journal and the IEEE Transactions on Sustainable Energy. He also served as chair of the IEEE Cyprus section. Even though Elias passed away in 2009, his research work continues to receive more than 800 citations per year. Elias's legacy remains very strong at the KIOS Center of Excellence and at the University of Cyprus. Not only was he an outstanding academic at the peak of his career, but he was also a beautiful and kind human being and a great friend. So every year we organize a KIOS Distinguished Lecture in memory of Elias. And this year, this lecture would be given by Professor Nikos Hatziargyriou. So thank you all for attending this lecture. And now I'm going to proceed to introduce our distinguished speaker. So Nikos Hatziargyriou is one of the world leaders in the area of power systems. He's with the National Technical University of Athens since 1984, a professor in power systems since 1995, and a professor emeritus since 2022. He is currently part-time professor at the University of Vaasa in Finland. He has over 10 years of industrial experience as chairman and the CEO of the Hellenic Distribution Network Operator, and as executive vice chair and deputy CEO of the Public Power Corporation, responsible for the transmission and distribution divisions. He has participated in more than 60 R&D projects funded by the European Commission, electric utilities and industry for fundamental research and practical applications. He has authored or co-authored more than 300 journal publications and 600 conference proceedings papers. He was the chair and vice chair of the European Technology and Innovation Platform of Smart Networks for Energy Transition, whose role is to guide research, development, and innovation to support Europe's energy transition. He's an IEEE Life Fellow. He's a past editor-in-chief of the Transactions on Power Systems and currently editor-in-chief at large of the IEEE Power and Systems Society Transactions. He's included in the 2016, 17, and 19 Thomson Reuters list of top 1% most cited researchers. He's the 2020 Global Energy Prize laureate. He's a recipient of the 2017 IEEE Power and Energy Systems Prabha Kundur Power Systems Dynamics and Control Award, and recipient of the 2023 IEEE Herman Halperin Electric Transmission and Distribution Award. So we are indeed very honored to have Professor Hatziargyriou with us today. I would also like to thank Mattheos Pantelis for making the connection and arranging for the visit. And I'd also like to thank everybody for participating in this important event. So, Professor Hatziargyriou, the floor is yours.
Thank you very much, Mr. Chairman, for the introduction. And good morning, everybody. I'm really happy to be here in your university after a long time and seeing so many friends. And I'm deeply honored to speak in memory of Elias Kyriakides. I have known Elias for several years as a member of the Power System Dynamic Performance Committee, where I was a chair at the time. And also, I have been a member of his promotion committee, I think at the level of professor, if I'm not mistaken. And also, Elias has visited us sometimes in Greece as member of PhD committees in the area of state estimation that I know it was his specialty. And of course, I have known his work from several of his seminal publications. So I'm really honored to be here today for this event. The title of my presentation will be Microgrids and their role in future energy systems. And let me just start by showing how the future integrated energy system will look like according to the vision of the European Technology and Innovation Platform of Smart Energy Networks. So you can see here that the future system will be fed by mainly renewable energy sources for electricity, also for renewable electricity and heat by biomass, solar, etc., renewable heating and cooling, renewable gas, renewable fuel, and now also there is a discussion about nuclear. And it will, the energy consumption, besides the typical households, tertiary sector, industry, agriculture, etc., will also include an increased electrification of the transport sector, and also both ground and also maritime and aviation. And in the middle of all this complicated system are the networks, where you see you have the old energy networks, gas networks, thermal networks, liquid fuel networks. And they will be interfaced through the various conversion technologies, like heat to gas and power to heat, power to gas, etc. Also the typical storage, various forms of storage, not only electricity storage, but also thermal storage, liquid storage. In the middle of all this complicated system are the electricity networks, which are the more versatile and effective. And in the middle of all these networks, electricity networks, is mainly the distribution system, because distribution is the field where most of the changes happen today. Transmission, of course, is undergoing significant changes by the introduction and interconnection of large power sources, renewable power sources like offshore wind, etc. But the main changes, the main transition happens at the distribution, where now we have all the new forms of energy being interconnected mainly, which means distributed generation, PVs and wind. Also, you have the demand side participation, you have the electric vehicles, energy storage, and you need more tools for an active network management. So all this creates a drastic change in the whole electricity supply chain. And the main really driving force for that is distributed generation. If you look at the IEA World Energy Outlook, the recent one, and how you see the various sources, various technologies being developed, it's clear that the solar PV has a tremendous increase until 2040. Coal is dropping, gas has some increase, wind is increasing also significantly. And so all these new forms of energy, mainly the renewables, mainly solar, is about 90% connected to the distribution grids, medium voltage and low voltage. So this new form is the one that creates the big changes in the distribution, in the whole power system. And this creates several operational problems. And the main problem, or the main aspect of the new system, is the challenge of flexibility, which means that as renewable energy sources and demand response are increasing at the distribution level, the system needs more and more flexibility. This is because the new forms of generation displace the thermal generation. And since the thermal generation is the one that produces the main flexibility for the system, which means the ability of the system to follow the changes in the generation and the load, this has to come from the distributed generation and other forms like distributed storage, distributed or demand side, etc. So you have new forms like renewable generation displacing most of thermal generation. Renewable generation requires more and more flexibility, and the flexibility sources are displaced. So you need more sources, and these sources are now mainly found at the distribution level. This means that you have more and more to exploit the distribution resources by the whole power system, which increases the value of the TSO-DSO collaboration, and also the need to balance demand supply quite significantly at the local level. So distribution networks operators also need to become much more empowered to use this flexibility, and also to be a basic actor in the whole operation of the power system. Another big challenge of our times is resilience, which means how you can protect the system from catastrophic events like weather events, like floods, like wildfires. You have all noticed how much at least Greece has suffered in the last years from wildfires, where very big parts of the country have been destroyed, burned. And this also, of course, affects greatly the power supply and the power system infrastructure and other critical infrastructures. In fact, as the European system is developed, which needs to integrate large parts of renewable generation, mainly offshore wind, from northern countries, from northern sea, and also large photovoltaic installations, the southern parts of Europe. This means needing a higher development of the mega grid, so to exploit the counter cyclicity among primary renewables, and also really exploit the physics. Where there is more production, it should be better exploited. In fact, you know that photovoltaic in Germany produces about 1/4 less generation, less power than a photovoltaic in Cyprus or in Greece. So also having investments optimized from a European perspective means that we need to develop more renewables at the time they have a better output. So the need of the European megagrid, however, also makes it more vulnerable to catastrophic events due to climate change. So another way of thinking of how you support the resilience of the system is to shift the attention from redundancy in assets to smart and intelligent solutions, which means enhancing more the local flexibility of the system, the local sources. And this means smart network technologies, demand response, storage, flexibility. So how you can enhance the supply to consumers during the event by employing smart technologies, operational measures. In fact, you need a balance between the two. As you know, enhancing infrastructure is much more expensive, might be effective. However, also being able to face the events during their happening is also can be a very effective way. Let me give you an example. For instance, just deciding to underground large parts of the transmission system or distribution system might be effective for wildfires. It's not effective for floods, or it's not effective for earthquakes. So you need some kind of optimal design of your resilience measures. In any case, microgrids seem to be now a form of distribution system that can play a significant role in these events. First, in providing flexibility, secondly, in enhancing resilience. First, let me clarify a few things about microgrids, which are also called the building blocks of smart grids. So microgrids are defined. There are several definitions, but the main components are here. They are electricity distribution systems that contain loads and distributed energy resources, which means distributed generators, storage devices, controllable loads, and can be operated in a controlled, coordinated way. Well, they can be operated while they are connected to the main power system or when they are islanded. So these red words, controlled and coordinated, are the key words of this definition that distinguishes microgrids from simple distribution networks with distributed sources. So you need to coordinate all these microgrids and make it appear as a unified unit to the upstream network. And this is not so easy. There are several technical challenges to achieve this. First, the microgrids have small size. So it doesn't mean that I have small problems. It's much more challenging to operate effectively small networks. They have different network technologies, different generation technologies, different prime movers. They have a lot of power electronics. Basically, they can be purely power electronic based, as renewables are power electronic interfaced. And this creates several challenges and also provides many more control possibilities. They can involve large imbalances between load and generation. So when there is a transfer from the interconnected to the islanded mode, you need to efficiently balance load with generation. You need to have load participation. You need new technologies. Also, the boundaries of the microgrids are not the same. For instance, normally in large systems, you have the frequency and the voltage being in relatively strict limits. In microgrids, you can relax these limits. You can play with DC microgrids or different technologies, since all these are interfaced in power electronics. Microgrids are mainly medium voltage and also low voltage networks, which means they have specific network characteristics. You can have large resistance to reactance ratios, which means that there is interaction between active and reactive power. And so it's important to see how you can control voltage by active power. It's expensive. There are issues of protection and the safety, the static switch that isolates the microgrid in case of faults. Communication is very important. You can't have the big systems, facilities of having big control, big computers. You don't have operators. You don't have dedicated operation in the neighborhood. You don't have expensive computers. And this also has another, this also creates a number of complex relationships among multiple subsystems that imply a hierarchical multi-layer approach for their control. As a control is the key word for microgrids. So multi-layer hierarchical structures means that you have a vertical arrangement of subsystems, priority of action from higher level to lower level, and dependence of the higher level upon performance of the lower level. And to treat that behavior, you need decoupling, which is more effective and more and allows a detailed study of the system and simplifies the mathematical formulation. So if you look at the microgrid, there are several levels of controllers that take action according to your philosophy. There is a microgrid central controller, which this is a typical microgrid, let's say, of a low voltage grid. And you see that the microgrid is interacting from the upper system at the low voltage bar. So you can think of a MGCC, a microgrid central controller, which promotes the technical and economical operation, sits on the low voltage bar. And then you have the interface with the various local controllers at the micro source and the loads. And the central controller can either provide set points to the various local controllers, or you can supervise them. And the local controllers are the ones that interface the control, they are the interface to control the loads and the DGs. So depending on the level of responsibilities you assign to the local controllers and the central controller, you can have a difference between centralized and decentralized control of the microgrid. In fact, the hierarchical control levels are, there is the primary control. The primary control, which is the fastest, maintains voltage and frequency stability and ensures proper sharing among the generators. So you have usually a decentralized loop controllers that provide several advantages in terms of plug and play capabilities, the local level. Then you have the secondary control, which is responsible for the mitigation of voltage frequency deviations. From the first control, it's fast, then this leaves some deviations, and the secondary control comes and corrects these deviations. And it can also facilitate the synchronization of the upstream network to perform optimal economic management, which is lower secondary level. And then you have the tertiary control, which determines the interaction with the upstream network and with the neighboring microgrids. So this is part of the overall distribution system. And now, so this is a picture of how these three levels interact. You have the grid level, the grid level is the tertiary control, the secondary control is the microgrid level, the primary control is the field level where the distributed sources are, and the physical microgrid. And there are different technologies and structures that can be thought of, which of course have different levels of complexity and different pros and cons. So you have, first of all, you have the centralized mode where a single controller manages and communicates the other components. So it knows all control inputs, collects all the information, runs optimization algorithms, and provides set points. We have the distributed control. We have the controllers sharing some information so that each of them has some knowledge about the behavior of the others, and this raises the overall performance of the system. And then we have decentralized control. This is composed of individual controllers which do not share any information. They understand what's happening from their own local measurements. And they provide, again, efficient control solutions, although they not guarantee their optimality. Okay. These different types of philosophies, which can be also shown here. Here, the central secondary control, where the central controller collects information from various DGs and optimizes and sends set points. You have the distributed structure, where you have some exchange information between neighboring nodes, and based on that, they can provide. They don't have the knowledge of the whole system, but they can provide local control set points. You have the third category, decentralized structure, where you have each DG, each distributed resource, performing its own secondary control and primary control based on purely local measurements. In that, we have to take into account first how the various DR controllers behave for primary control. You can have grid forming and grid following distributed resources. In the grid following resources, all you do is to follow the P and Q set points, the active and reactive power set points that you need to follow for the optimal operation of the system. While when you run in an islanded mode, so one of your controllers at least needs to run in grid forming mode, which also sets the voltage and the frequency. And this simplified diagram shows how by measurements of the system you can apply grid forming and grid following control actions. In fact, even if you are a grid following distributed resource, again, you can provide voltage and frequency support control. This has been done also we have studied that also in some Greek islands. Now, in the next slides, I have tried to summarize these basic control techniques, and I'm not going to go into too much detail on this because it needs a lot of time to really explain in detail what is happening. So I will go a bit fast in the next slides. But in few words, the primary control can be done through communication or communication-free methods. So in the communication-based methods, you can have some concentrated control or master-slave control. You can have some distributed control. While when you have the communication-free methods, these are used on the conventional Druck control. And the Druck control has some of its problems that can be solved through various modifications of this. So just to explain some detail, the primary control means that either you have a centralized scheme, we have a controller, a central control unit that provides set points to the various, defines the set values of the current for each module, for each distributed resource. And you need a communication link between the central controller and its unit. It suffers from single point failures. The master-slave control, this you use a controller, a master-slave that operates also as a voltage source converter, regulates output voltage, and provides set points also to the various other slave controllers. Distributed control means that there is no central control, but each of the controllers has an additional current loop to enforce its converter to track the same average reference current. Requires a current sharing communication bus and reference synchronization for the voltage. And then you can have communication-free methods. I wanted to say in this slide that I jumped, that here the impact of communication is very important. And obviously communication introduces delays, package drops, etc. So this can affect the stability of the system, and you need high bandwidth communication to be able to operate the system in a centralized, using centralized control techniques. Communication-free methods are based on droops. They emulate the operation of the typical thermal machines. What happens here is, of course, once the load changes, the DGs carry larger load based on their slope of these curves, which model the change of power compared to the change of frequency. And this is proportional to the, as you see from the relationships, from the installed maximum power P and Q. And this works well in large power systems. However, in distribution systems with large resistance over reactance, this cannot work because then this frequency and voltage are not decoupled. In fact, frequency is more dependent on active power. Frequency is more dependent on reactive power and voltage on active power. So there are several techniques now, like using, for instance, expressing these slopes as voltage dependent on P and as frequency dependent on Q, or other more sophisticated techniques include using a virtual impedance approach, where you put a virtual impedance in the loop to change the resistive lines to inductive lines. So this is designed to be bigger, does not have losses. In fact, changes, provides this virtual impedance that again decouples active from reactive power. And, or you can use frame transformation methods that in the new transformed framework, P dash and Q dash, based on this current, on this angle transformation, can depend on the relevant on the classical, let's say, magnitudes. So, what's the comparison between the two methods is that in the primary control approach, the communication-based methods are more accurate sharing. The system parameters, however, should not be known. They have good dynamic response. However, they have low reliability because they are centralized. So if you lose something, you lose the system. Low redundancy. Communication network is important. You need high bandwidth. While for the communication-free methods, they are modular and flexible. They are important for plug-and-play operation, and they are more resilient against their outages. However, they are less accurate, and they have reduced transient performance. So this is regards the first level control, the primary control. If you look at the secondary level control, again, here you can distinguish between communication-based methods and non-communication-based methods. This secondary control is the one that needs to maintain stability, mitigate the transients and the mismatches, and to have a proper active and reactive power sharing. So in that case, the main methods are again centralized, distributed averaging techniques or consensus techniques. There are non-communication-based control, which are filter-based, destination-based. So what you mean here that the secondary control, what you need to do is to push this drup to the upper level so you can compensate for the error that happens in the primary control action. Okay? So in the first case, you can again use a centralized secondary control, which again means that the MGCC gathers the data, performs calculations, and provides set points how you move these drups. You need extension communication, but now you are much slower. So you can use a lower bandwidth. Again, this system suffers from single point failure. If you lose your MCC, you lose your secondary control. Reduce scalability. If you add a new unit, you need to update the settings. Sorry, while you distribute control, you don't need an MCC to coordinate the units. And what happens here is how you find, of course, how to balance the system. There are a number of techniques. There's an averaging technique, so it's converted, computes secondary terms using measured values of all or some of the other inverters. You calculate the local frequency and send to all other inverters the average frequency. These are known also as gossip algorithms. Based on that, you can calculate the average frequency and adjust your drup so you end up with the average frequency. Or you can use what's called consensus distributed control, where you transmit measurements and through a form of consensus, you can again end up in the common frequency. And then you can also apply communication-free methods, which in this case, you calculate the secondary control with local measurements and without communication. And then the main idea is to decouple the dynamics, the primary and secondary control loops. This is done by a suitable filter and a typical filter is the washout filter, which allows you to find locally how to adapt, how to adjust your frequency. Or you can use also state estimation techniques. So each of the local controllers and secondary control, by running a state estimator, can, based on its own local measurements, can find how to control the voltage and frequency. So having just gone very, very quickly, and I'm happy to go back and discuss details if you want, of any of these control techniques. There is a very large literature on control of microgrids. I can say that from all the actual applications I know, at least, there are most of them, or all of them, are based on centralized techniques. So you have a central controller, MCC, that finds how to operate the system optimally and sends set points. One of the very few exceptions is the KIOS microgrid that was installed in Greece more than 20 years ago, that it has been used for several tests, also from NTUA, who have tested various innovative technologies. And this is an isolated microgrid with 12 summer houses that includes a number of distributed energy resources, PVs and storage. And there are some diesel units, a diesel unit that is only used for backup. So we want to achieve 100% renewable penetration, operation. And I'm telling you, this would happen more than 20 years ago. And an important component is that it has a number of flexible loads. that are mainly the water pumps, because the place, except no electricity, has no water, so we use pumps. And we have applied intelligent control techniques, which means local agents, intelligent agents, and I will tell you how this is done. So first, a few things about the installation. This is, for instance, one of the houses, and you see on the slope on the mountain, on the hill, some of the photovoltaics. There are photovoltaics in most houses. They are, as I told you, there's a 9 kVA diesel that is only used for backup. There is storage, flexible loads, and quite advanced Sunny Island inverters at the time from SMA. And what we have installed are intelligent load controllers. So for each house, we have installed load controllers that were using the wiring of the house to control the air conditioning and quite heavy loads, and also the water pumps. So the idea is, as the system house is the one that has the main, is the MCC, the microgrid central controller. It's where you have also the batteries and the control system that could send signals to the local controllers. So you have the PV and the diesel and the batteries. And then the agents that were installed in each of the houses in the intelligent load controllers could identify the status of the environment, which means the available energy in the battery system. And then by negotiating, exchanging messages among the houses, they could decide how to share the available energy without central coordination. This is perhaps one of the first systems of decentralized intelligent system control for this type of systems. That was, in fact, quite successful. And in fact, it had a number of positive influence also on the local people, because in the past, it was people used to behave, let's say, more greedy. Whenever they were there, they tried to use the water pumps, exhausting the PVs, the stored energy in the batteries, while now there was a more fair, let's say, technological system that would share fairly the available energy. And it was also able to decrease a lot the use of diesel. So just this is not my final conclusions, but just to say that there are microgrid structures that are ideal to coordinate distributed energy resources, distribution networks, and they are a key for decentralization of the power system control. So we can think of the collaboration between central systems and local distributed systems to face the system challenges, mainly the resilience issue and the flexibility issue. Control is a very active area of research in the last years. There have been various techniques developed, and there are many techniques besides the ones that we have very briefly gone through. There are also advanced techniques, including model predictive control, reinforcement learning, many methods that are really very interesting from an academic point of view. In practice, as I said, mainly the actual installations are using decentralized control techniques. I will complete my presentation by some discussion on the benefits of the microgrids. And you can see in this diagram that microgrids are really beneficial in several aspects. First of all, obviously in environmental benefits, because they are based on renewables or on very efficient gas units sometimes. So they obviously lead to greenhouse gas reduction. They have economic benefits because they can have a local market value. So you can think of benefits operating local markets to provide flexibility and other services, or to exchange energy between the participants in a peer-to-peer fashion, for instance. They have an aggregation value because as there are many resources, small resources, you can think of them as an aggregated, more substantial value of energy that can be interact with the market. They have network hedging value because since they supply load locally, they can infer, they can delay infrastructure investments in larger transmission distribution networks. Also, they have technical benefits. They can be used for peak load saving, for voltage frequency regulation, for energy loss reduction, for reliability enhancement. This is very important because when you have a problem upstream, you can isolate the microgrid and make it supply critical loads, so that's beneficial for all people involved, consumers, system operators, their owners, etc. So the question is who will develop a microgrid and who will own and operate it. So there are different categories of microgrids in that sense, depending on the ownership. There's the utility microgrid. The DSO owns and operates the DR and the microgrid. Also, depending on the regulatory environment, the DSO might also provide retailing functions, selling electricity. This is not possible, this model in Europe, where there is deregulation of network activities from retailing activities, or competitive activities. So in that cases, regulators tend to restrict the utility control of microgrids beyond the pilot phase projects, although their ownership has been granted in some states or countries for resilience or for enhancing flexibility. So in the US, there is quite common for utilities to operate microgrids and use it. There's a number of very good examples. And also, I think in Europe, if you manage to prove that the microgrid will only be used to enhance flexibility or to enhance resilience, this should be again revisited, this decision. Now we have a single owner or aggregator microgrids. This is the case for a single entity, like an industrial complex, a university, a military camp, or an airport, etc., owns several DRs. And then an aggregator maximizes the value of the aggregated DR participating in the energy markets. This model can be applied, of course, where there is one owner that can collect and aggregate all resources and again play in the market for some profits. And there is, let me before going to the third category say that there are several advantage services that the microgrid can sell to DSOs. So apart from peak saving, voltage control, islanding operation, black start. Again, black start is very important for the resilience issues. When there is a disaster, how you can black start the system from bottom up, or then you can build microgrids to help with also the overall system restoration. But also microgrids can, this is happening in US, this what I'm describing to you here. Also microgrids can offer services for EVs. So they can provide fast charging at dispersed locations where it's difficult for the transmission network provide the capacity. We can have a local supply of EVs. You can have optimal placement of charging stations, local generation resources to mitigate overloads and bottlenecks. You can have low-cost generation mixed for fast charging of EVs and truck fleets. You can have optimal charging and discharging to minimize the overall costs and to mitigate the impact of grid outages on the EV charging schedules. And there's a new idea now that is quite a lot discussed, how you can use microgrids to produce hydrogen. So you can think of places where the network is quite weak, but then you can, by installing a larger local renewable resource. You can use it for producing hydrogen, for installing a rather large electrolyzer. And this, for instance, is something that is discussed for Africa. You can produce hydrogen in these natural conditions that are quite weak. But an important really thing is a community microgrid, where the group of consumers, including prosumers, own and operate DR, including now the amount of distribution assets due to the multiple interconnected customers. So if you want to minimize electricity bills or maximize revenues, forming local energy communities. Local energy communities is something that is sometimes confused with microgrids. To my opinion, microgrids can be the technical base of local energy communities. And especially when the local energy communities are able to own network infrastructures. There's a lot of advantages of local energy communities, as you know. They have been promoted also by the European Commission officially, although it's an old story for you. So they are an association or cooperative or a partnership, a non-profit organization and other legal entity, which is effectively controlled by local stakeholders or members. They are value rather than profit driven, and they are involved in distributed generation and performing activities, distribution system operator, supplier, aggregator at local level, including across borders. There is a lot of movement of local energy communities in Europe today. In Greece, this has been a very popular and successful development. Now we have more than 1,400 local energy communities registered. And it's worth really looking at the interaction and difference and synergies between local energy communities and microgrids, since both promote decarbonization and decentralization, both require optimal coordination of the energy resources. It's difficult to compare the two concepts because microgrids is more a technical focus, while local energy communities are social and economical organization of the community consumers. In microgrids, you need to speak about distribution assets, which is not the same for local energy communities. There are striking differences when you speak about utility microgrids or single owner aggregator microgrids. However, if you speak about the community microgrids, then the differences become blurred, and I believe that there is a lot of value of these two communities to exchange all technological developments that have happened in the last years. So now my overall conclusion is that the microgrids are the building blocks of smart grids. There are numerous advantages that can be provided by the effective integration of DR for network operation, for prosumer participation, for retailers and aggregators, for environmental protection, for social welfare, etc. It's very important that they can provide excellent capabilities for provision of flexibility and resilience. There are numerous technical challenges also, but there's a number of promising solutions that are being developed. It's a very active field of research now worldwide. And it's also important, to my opinion, to look at how microgrids can support, besides the other applications, the development of local energy communities. So thank you very much for your attention. This is a number of my PhD and postdoc researchers that I have been working on microgrids in the last years. And this completes my presentation.
Here in the case of the grid forming approach, we're actually relying on this step that actually are responses to the reactive. So we are waiting for a frequency deviation or a voltage deviation in order to provide that reactive power of the phenomenon. However, in the numbers, the inverters are able to operate at some milliseconds. We consider that we should somehow move in or proactive start posting in order to not wait for the frequency variation react. In case that we go into this direction, it will be, let's say, compatible with the typical conventional generation plants.
Yeah, these are very interesting questions that I'm not sure they have been answered. Okay, so there is quite a lot of research now on how you can coordinate grid forming inverters, how you can also coordinate classical thermal. Now we speak about the distribution level, so you cannot think of the large thermal, but you can think of the local thermal like diesel, etc. So how you can coordinate this group approach for the several resources is an open issue. We have tried to do some research in that, but so it's interesting because of the distance and also the setting of the various control parameters affects the stability and of the system. So it needs careful tuning. Now, of course, power electronics can provide a lot of, can support the system. As I said, also in grid following mode, there are parameters that you can, there are control supplements that can help the support of the voltage in low parts of the low voltage parts of the network. So I don't, well, at the medium voltage level, I don't know of any real application. There have been some applications in the high voltage, especially in the large HVDC lines, and that are used to support the network, yes. But still, we are far from the low voltage and medium voltage level, I believe. But it will come because you need that now.
Thank you, Professor, for the presentation. Can you elaborate more about the tertiary controllers? I mean, what are the objectives of these controllers? And if there are different objectives, if you would consider the islanded mode or the connected mode?
Sure. The tertiary control, I did not mention that at all. Tertiary control is what the DMS system does, how your controller interacts with the overall distribution optimization. So this only follows what the DMS requests the microgrid to do. The DMS might, for instance, request that your microgrid provides a certain P and Q to support the system. Okay, so that's the overall optimization of the system. Or it can be used tertiary control to coordinate with the neighboring microgrid to see how they will serve the command of the distribution management system. What was the other question, sorry? Yeah, of course. As you understand, when you are interconnected, the only thing you need to do is to provide the P and Q that is requested from the upstream network, or if you play in the market, how much you must output for your market bid. In the islanded mode, there is no market issue, but you need to ensure that you maintain the stability and the frequency. So that the grid formed inverters play the major role. And of course, you need then the power setting, etc. All the techniques I showed to you were mainly were mainly referred to the islanded mode when you are non-interconnected. Island. This is the more difficult part.
Thank you. Quick question in the business microgrids, that you use the water pumps as flexible demand. It also model the water distribution system on the island in an optimized manner, or
there is no water distribution system in this. Everybody has its own well.
I would like to have your opinion on the DC microgrids. AC microgrids are, I would say, well established, let's say, configuration and agreed. There are several calls now through the European Union and the Commission for DC microgrids. What are the benefits comparing the two, and whether we are near the adoption of these DC microgrids based on the current configuration of the grid now?
Yeah. People claim that DC microgrids are more efficient, and this is understood because you don't have the losses of the reactive power. Of course, the difference is you don't have any more voltage, so you must operate the system based only on frequency measurements. Now, regarding actual installations, I know that ABB is interested, and there's a pilot of a neighborhood in Finland. There are some activities in India, but I don't know how far we are from real installation. Also, of course, the major problem is the protection, because you don't have the waveform to see when to open. So there needs a special protection equipment. There is research on all that, and I'm not really aware. I have not been involved deeply in any DC project.
Now with the advancement of monitoring and control, we have the ability to do much faster control that we used to be. Significantly much faster. And this challenges some well-established assumptions that we consider in our modeling of power systems, because traditional power system modeling is based on this quasi-steady state assumption on the power lines, on how we consider lamp-side models. I'm wondering if this aspect is something that you come across, or if you have seen any practical challenges arising from this assumption as well.
I guess this is a general question, not related to microgrids, right? Because microgrids do not have the luxury of having very advanced infrastructure. Think of a neighborhood with a few houses. They cannot have the luxury of very sophisticated measurement units, big computers, fast, large bandwidth operators. This doesn't exist, okay? So
these are also connected to the grid for this.
The grid, yeah. So what was the question now exactly? I mean, of course, there are many advantages now, very advances in all this. Protection and WAMPs and things like that.
I was wondering if this fast control action could interfere with phenomena that were considered as, well, until recently in a different time scale, so weren't considered, such as electromagnetic behavior in the power lines, for example. I mean, we could make this quasi-steady state assumption.
Okay.
This is in almost all texts, so I was wondering if you came across any challenge for considering this.
Yeah, for sure, power electronics have had a tremendous impact on the dynamic behavior of the system. And you now need to, depending on the phenomenon, you need to use now EMTP type of tools, electromagnetic transients, rather than using phasors, using this steady state approach, this semi-steady state approach. There has been a very good report from IEEE that is entitled Power System Stability Revisited and Redefined, which explains how the power electronics have changed the way the system behaves in all forms of stability, the classification of stability, which is, of course, the voltage, frequency, and rotor angle stability, and converter-driven stability, and also the interaction of the mechanical system with the electrical system, which was mainly, of course, the resonances, but the electromechanical resonance, etc. All this needs to be now rethought and redefined, and the tools are now very different. So indeed, there has been tremendous changes how you model the system now. And if you speak about such time scales where you have the electronics operating, then the reaction of the lines, the capacitance, and all this also needs to be taken into account. That's why using EMTP now makes sense, much more than using the semi-steady state analysis, the phasor analysis we used to exploit so far. But look at this report. I can send you the information if you want.
Thank you. Okay, one last question there.
That's it. Thank you, Professor Hatziargyriou. That's a very interesting talk. I have it's basically a clarification I would like to get. You mentioned about communication through microgrids earlier. Does this mean that these microgrids will be fully autonomous and they shouldn't interact at all with the DSO or any of the network? If so, then how would it work in energy communities like microgrid communities that they will have to report back to the DSO if it's communication free?
Let's not confuse the issue of coordination between the local energy community and the TSO and the technical requirements for the infrastructure of communication for control. These are two different issues. So yes, indeed, there have been experiments and there have been designs that you see that the DGs, the distributed generators, are behaving autonomously, optimizing. It looks a bit spooky, but it happens. You can have the various controllers being operating without control and trying to optimize the operation of the microgrid without central coordination. Of course, there are several centralized algorithms, like I showed a couple of them, consensus algorithms or averaging algorithms that try to find the average frequency and try to go the system there, to drive their system there. There have been this type of. So, but this has nothing to do with how you communicate with the DSO, and of course, this needs to be done. Thank you very much.